Good evening, everyone. We are live. I'm here with Scott Walter once again, and today we've got hopefully a fun conversation lined up. We are going to continue. So, Scott and I had a great conversation with James Douma a few weeks back where we started asking the question, as Tesla develops FSD and the Optimus robot, that will obviously give them a lot of new tools to put in the toolbox. And as Elon has always said, the factory is the product. And so when they have new tools in their tool belt, we assume that they're going to use that to the best effect that they can. And so we think that there's going to be some interesting evolutions in the way that Tesla manufactures both the bot and then their vehicles as well. And today, Scott and I are just going to start playing with that. You know, we obviously don't have any inside information, but with Scott's experience, having worked with a lot of automation in a variety of industries, but automotive included, we're going to start thinking about what are the steps between here and a potential alien dreadnought type future where everything is automated and we don't necessarily need human labor in order to produce things. But, you know, we've got a long ways to go from there. And so we kind of know what the current state is, and we can hypothesize what it's going to look like in the near future as they start adding the ability for not only Optimus, but even the current automation hardware that they have, like the KUKA robots or any variety of industrial manufacturing robots. If we give those things the ability to see and act intelligently based on their surroundings instead of just being blind and hard coded, how is that going to change the way that Tesla can manufacture higher quality products better, faster, at lower costs? So, yeah, thanks for joining me this afternoon, Scott. And yeah, I'm really looking forward to this conversation. So I'll just turn it over to you.
Okay, thanks, Hans, for having me back on. And if the audio quality has suddenly improved, you can thank Hans for that. He helped me debug a lot of the issues with my mic over the weekend. If not, I'm still to blame. Okay, so again, thanks for being so patient with me, Hans, on that. Yeah, to sort of pick up the conversation is, you know, one of the things that Farzad keeps on saying is the robots are coming. And I think the other day someone said, no, the robots are already here. And he's kind of right. The robots have been here. And technically, I guess you could say they've been here since, I think, 1960 or 1961, when Joe Engelberger sold the first industrial robot to General Motors. And so that was like the first time that actually a piece of equipment had the label robot. And that also was a back and forth because GM didn't like it being called a robot. They thought that was like too science fiction and they would be laughed at. But Joe Engelberger said, you know, he stuck to his guns and he insisted they had to call it a robot or else he wouldn't sell it to them. So that really goes back to the first programmable mechanism that we consider to be an industrial robot. And then we have all sorts of these different mechanisms out there nowadays. And there's a big debate on what actually is a robot, all right? I've had this back and forth with James Douma and everyone else that, you know, he refers to his pool vacuum cleaner as a robot and tell him, no, it's an automated vacuum cleaner. I have the same arguments about a Roomba not being a robot. And then there are some of these definitions of what they are and are not. So we used to always think of these things that maybe look like an alien or look like an android, but really it's some kind of arm, and it has to have at least 3 axes of motion. So you can have a lot of automated equipment that might have 2 axes, and that might count in there and everything else. And the RIA set up these standards of what counts for a mobile robot and the type of industrial robot and what these cobots are and everything else. But for the most part, we should think of it as a piece of manufacturing equipment that's very flexible and very easy to reprogram to do another kind of task, multiple tasks. And that was sort of like my issue with the Roomba is like, well, there's a certain amount of programming in there. It can do one job and one job only, and that is like vacuums. Whereas the idea is that a true robot should be flexible enough to do different kinds of tasks, not always the same one. But they're not really used that way. They're more set up as a piece of flexible equipment that can be adjusted to do a particular task and then do it for a couple of years in a row, okay? But the same robot can be put next to that one and do a different task, and another one, and another one, another one. So it's used in a very different kind of flexible way as opposed to one robot which is doing hundreds of thousands of different activities. And if you think about it, we do that every day. I mean, if we consider ourselves a robot, we get up in the morning and we make our bed, maybe we make our breakfast, we brush our teeth, we pick up a few items here and there, we get in the car, we drive somewhere, we go to work. We're doing these different tasks. But if you go into a factory and look at the orange and yellow and red and blue robots that are in there, you're going to see a lot of those robots just do the same task again and again and again, and they never do anything else. And the only time they do something new is if the product changes. And then when the product changes, someone has to go in there and tell that robot what the task is, because the robot is really just repeating the instructions a human operator gave it months or years before. And every now and then someone will come in and just make sure the robot is still kind of doing what it's supposed to, and any maintenance it needs to have, and do a little bit of touch up because it might drift and other things because of wear and tear, or the tooling needs to be maintained. But for the most part, it's just doing it again and again and again. You got to reprogram that. So robots have programs, and I think we all know what programs are. Anyone who's done Python programming knows, like, you write down a list of instructions and the computer will interpret those things and it will perform some sort of task and activity. For a lot of people who first get into programming, it's a difficult concept to understand because it's very abstract. You're looking on the screen and there's a bunch of text and you run it and it creates some output, and it's just like mysterious and you don't quite get it. And I understand, because it's manipulating all these symbols and it's producing something. Usually it's spitting out some numbers. You're like, so what? Some of us are more visual learners. We like to see something. And so robots have a program which is very easy to see. And what that is you see the arm goes over to there, and then it goes to there, and then it goes to there, and it goes back, and it does the same movement every time. And somewhere along the way, it might perform some activity or may be able to change the speed and everything else. And when you see that program and then you see what the robot is doing, suddenly you go, aha, now I understand what programming is. So robots run on programs. Python scripts are a type of programs. ChatGPT is able to write Python scripts. So it shouldn't be a big stretch to imagine, could an AI like ChatGPT start creating robot programs? And the answer is absolutely. There's no reason why it cannot, because conceptually they're no more complex from the semantics and the grammar that's in there as a Python script or a JavaScript or C# or C++. In many cases, they're actually simpler because the people who are using it aren't actually programmers. They're robot programmers or they're CNC programmers. So they're very visual, they understand what's going on the floor, and they can record these steps. The difference is one is working in a very abstract space and the other is working really in the three-dimensional world where you have to understand what's going on. So there's certain knowledge base, there's some other things, but there's no reason why the AI cannot do that.
And then another example that, might be easy for some of our listeners to grasp is if you've ever written macros for Excel, and you think about what goes into writing a macro for Excel, a manufacturing step that one of these robots does is essentially just a different form of like an Excel macro. And the other thing that if you've ever written an Excel macro you might have experienced is that if you assume something about your spreadsheet that ends up being incorrect, or one time when you run the macro that assumption is not valid and it messes up the entire script and can wreak havoc on your spreadsheet. Well, the exact same things are true when you try to program one of these robots. And if the conditions are not just so, if the part that you're trying to pick up is not in the exact correct place, or if the end of arm needs to have access to something and there's something in the way, that it doesn't have the ability to realize that the assumptions that the programmer made when they created the program originally are not good assumptions in this case, and they don't have any ability to adapt and do anything that is intelligent to deal with changes in their environment.
Correct. And so another term that's sometimes used for the robots that we see on the shop floor is they're called a manipulator. So a lot of those say, get the manipulators over there, or the robot manipulator. And the reason why they mean that is because it's able to manipulate objects. It's picking up objects and moving them around. That's basically what it does. And some of those manipulations may result in a certain process occurring. So it's able to execute these different processes. But the main thing is that it has to pick something up and move it off somewhere else. In the early days, when computers were not very sophisticated and we didn't have vision systems, the only way we could get something like that to work is that the part it's picking up always had to be in the same location. So it's more or less the difference between watching a play and watching a movie. Once the movie's been recorded, every time you watch that movie, it's the exact same movie. That movie never changes, unless you're in one of these weird Woody Allen movies where he's watching a movie that changes, but that's a different story. But if you go to see that same story as a play, it's different every night because the actors that are in there are able to ad lib a little bit. They're able to read the audience. So it's like, it's sort of the same script, but you'll notice it's changing a little bit. Now, what's happening on the shop floor is basically you are seeing the same movie again and again. The robot is out there. It's been taught a certain set of tasks and it plays it back faithfully because it doesn't know anything better. So if it's going to come over and come down and close its gripper, either the part is there or it's not. So if you put the part in a different location, it's going to miss it. So you have to make sure it comes in. So if it's coming down to a conveyor system, you got to make sure the conveyor system is able to lock it into the right place, have a sensor which will say, it's there, you can do it. So that might be as sophisticated as it gets. Not necessarily a camera system, but literally some sort of trigger, which would be the same as like your garage door opener, the photo eye that's in there. As soon as it breaks, it'll say, hey, I see something. And now that it knows it sees something, the robot will get the signal, wake up, come over, and go down and repeat those steps exactly, pick something up and move it over to where it is. So in order to make sure the parts are where they're supposed to be, you have to have the right kind of tooling, you have to have the right kind of fixturing to make sure it's in there. And that's where a lot of cost goes in, is to make sure you are corralling those parts exactly the way they're supposed to be, so that when you go over with your eyes closed, it's always in the same location again and again and again. And you do that hundreds of thousands of times. So generally, that's what happens in automation, is that you can break it down into three areas. Automation where, let's say manufacturing, where the batch size is so small, it does not make sense to automate at all. It's purely done manually. And then when you get up to a certain size, you might say, we can start introducing some kinds of automation. And the automation you might put in that point is what they would refer to as flexible automation. Automation is very easy to set up, and it's able to be maybe a little bit faster, a little bit more accurate than manually, but not quite as good as hard automation. Because hard automation, you can go really, really fast, but it's just really able to do one thing and do it really, really well. But at that point, your batch sizes have to be much higher. So when you start getting like in the thousands or tens of thousands, you think flexible automation. When you start getting above 500,000 to 1 million, that's a transition between flexible to hard automation. And so those are some of the decisions you're going to make on whether you're going to go ahead and do that. What makes it costly on the lower end is not so much that the robots are expensive, but it takes just so long to program them, to get them up and running, and the fixturing you might need. You'd like to say, well, the reason why you can do it manually is I don't really have to show the operator what to do. He knows what to do. You just put the part there. They just, go and they read some drawings and some other things. They understand it. They go ahead and do it. They knock it out. And so what you'd like to have is something that has the intelligence to interpret what it is you want to do, and also the capability. And so the robots are capable. They can do small batches. They really can do small batches. The problem is the time to program it is a lot longer than the time it would actually take for someone to build that part manually. And generally, the cost hourly of the programmer that's going to be going over the teach pendant will probably be more than the manual operator. So like you sit there and you do the math, like, okay, which is going to be the best way to do it? Obviously, you stay manually. So if you want to drive the part counts down, or if you want to drive the cost down and be able to do more and more flexibly with a robot, you need to find a way to be able to improve the programming speed. And that's basically what I've kind of dedicated my career the past 4 decades to being able to do that, because that has been the problem with robots, industrial robots, since the early 80s when they were brought in, is trying to find a way to program these things as quickly as possible.
And so now what do you think the next step is, based on the technology that you see that Tesla has, in reducing that, either, just going one shot straight to giving some form of intelligence to the robots themselves so that they don't need to be externally programmed? Or do you think it's more likely that we'll see in the short term them just continuing to make the ability to program the robots faster and easier?
Okay, it will get faster and easier once they sort of figure out how to get Optimus to work. So the way I look at it is that the training that they're doing with Optimus, they're going to learn a lot. And eventually what they learn from that, they are going to move over to the industrial robots. So it's not like there's this extreme urgency to be able to program the industrial robots this way. That's going to happen. And it's the question of whether Tesla ends up doing it themselves or whether the robot vendors themselves start realizing that, this is the kind of capability we need to start putting in and start talking about that to Tesla and everyone else. Because trust me, I'm not the only person that this has occurred to. I mean, when you brought up with James Dalma, he was like already on board. He'd already thought about that. I'm sure a lot of others had realized that you can go ahead and do it. Now, I don't want to make it seem like the industrial robots are totally stupid and can't do anything, because they've added more and more intelligence as they've gone along. So at first it was, they had absolutely no eyes, no capabilities. And there's still a lot of robots operate out that way because the parts always coming in the same place. It's the same thing. They can just run that way. And with their eyes closed, there's no need to put camera systems in there. But there are examples where you do need to have a camera system in there with a robot. And so cameras will be used to adjust the location of a part or identify a part. A part might come in, and the robot needs to know, well, I'm able to do a half dozen tasks. What's the part I'm working on right now? And there could be a variety of ways. I mean, it could be a simple RFID sensor that tells you it's part A or it's part B. But the other is it might just recognize the part and say, oh, it's this. The other is that it needs to know the position and orientation of the part. So a lot of times we have a program which is in the work, let's say the coordinate system of the workpiece or of the part. And so long as we know where the part is, we can adjust our program with a simple transformation. Say, oh, it's over here now. I now just do those movements. So if I need to do, some sort of circle movement on top of something, or draw, let's say, 4 holes on top of something, I know how to draw those 4 holes relative to each other. I just make sure that that first hole is in the correct position with respect to the workpiece. And I can get that usually with some sort of sensors or with a vision system that will tell me that. We have other examples which have been around for a while. One of the more famous episodes of I Love Lucy, you might remember, has to do with the chocolate factory. Lucy and Ethel are in the chocolate factory, and they're trying to pull the chocolates off of the conveyor belt. And you actually have production lines like that where chocolates are coming off a conveyor belt and they have to be taken off and put into boxes. Well, there are robots that do that. And these chocolates are coming off these conveyor lines in random positions and orientations. So that means the robot has to identify a target. Which one is it you want to have? And it has to look at it. It's like it has to be within some window. So if it's within this window, I have time to get to it. If it's outside the window, there's no way I can get to it before it's already gone away. And the next robot next to me is going to go ahead and get it. So it identifies a target, it jumps down there, it picks it up, and then it goes ahead and it puts it in a box, and we'll have like a box of chocolates, with all the different positions in there, and it knows which ones are full, which ones are empty. And it may be you have some heart-shaped ones, everything else. So the heart-shaped ones are coming out and they're in some random orientation. You got to pick it up, you got to figure out the orientation, come over to it. And you have vision systems that are doing that, sending that information to the robot, calculating the program, making adjustments, goes over and does that. So those are kinds of examples you are already seeing out there that seem intelligent, but it's not AI. It's just a really clever written program. The closest thing you'd have to AI would be the fact that you have these vision systems that are able to identify everything. But that's been around for a while, well before there was AI. I mean, there was all these edge detection and convolution algorithms, everything else people were working on the 80s and 90s to try to figure this stuff out. So they've been very good, except a lot of times they only work with 2D with certain lighting models and everything else. Now with the more sophisticated AI, you will just be able to have it almost figure out exactly what it is you want to do the same way the human is able to do by looking at it and say, oh, that's what you want me to do, right? And go over and do it. So programs can be adapted, but what we want to do is look at the bigger picture of, I've got a product changeover that's coming in here, and either I want to use the robots that are currently out where they are on the shop floor. So maybe like we've seen the welding robots that are doing like the Model Y and the Model 3. Potentially if we make a change to it, oh, it's the Highland is coming out. Well, now if the Highland's coming down that line, we could probably use the same robots, maybe in the same positions, because it's almost the same size car body. But there are going to be some welds that are a different position, and maybe we just need to go in and tweak those welds, or we need to add a few or remove them or kind of change them around. So you might want to be able to say, how would we do that? Well, right now, you're going to hire a bunch of programmers that are going to go out there and get to figure that out. And they're working on it. They're trying to figure out what's the best placement for the welds and everything else. At some point, they might come to the conclusion, oh my gosh, we have to actually move one of these robots or redesign the cell or something like that. It would be nice to have the AI go through and figure that out and just say, yeah, we can reuse a cell. Or like, oh, no, we're going to need a new line. Or you just need to move one robot. Or, hey, guess what? If you kind of move a couple of these robots around here, we can take 2 cells and turn them into 1. So there's all this optimization, but a lot of times you don't have the luxury of optimizing the cell to your heart's content. It's more or less, we got a schedule. We have to have this product off the line by early September, which is usually like the new model year. So you're dealing with those constraints, do whatever you can, and you'll accept a certain amount of, let's say, inefficiencies just to make sure you get it out. But if you get the AI that's able to go through there and start looking at all sorts of different combinations, it might be able to say, hey, there's a more efficient way of doing this. And a lot of the problem, of course, is that you might get those robots in really close, the closer together, the more they can work. Well, at some point, you've actually got workers that are going in there and trying to program these robots, and they've got to get right down and actually see what's going on. So you got to give them enough elbow room to move around. So you've got to kind of remember those space requirements. But eventually, you could start programming these things with more intelligence, and that is a system that understands the three-dimensional world, understands these programs, which are very simple, and then is just able to go ahead and put them together. So that's why I think you will be able to move that way, and you'll save a lot of time, you'll save a lot of costs on the programming, and eventually have situations where your tooling may be able to be less expensive because you're not worried about the rigidity of making sure your parts are always exactly where they are and a fixturing to clamp it down to make sure, oh, I've located exactly where it is so I know I can grab it off of that. So I can kind of come in roughly in the right area and just go roughly pick it up and go ahead and move it.
And that type of flexibility is also, basically the same type of flexibility that it's needed to, no pun intended, deal with flexible objects like wiring and cables and those things that tend to be very difficult to use any automation to actually manufacture.
Yeah. The first thing is trying to figure out the end of arm tooling that can actually pick up something that's flexible. And depending on what it is, you might use like a vacuum gripper or something like that as opposed to a tactile gripper. So if you've got like cardboard, which is, let's say, the most common flexible object that a robot will be picking up. And the reason they'll be picking up is you might have a palletizing situation where you're putting boxes onto a pallet. Well, the boxes are already, something that's made out of cardboard. But a lot of times you have a separator sheet in between it. So you'll have a stack of them over somewhere and the robot has to go over and get them. And now the robot has got something that either tells it how deep that stack is, or it's kind of counting in its head. It's like, well, I know each piece of cardboard they're putting in there is a 1/4 inch. And so after I pick that one, it means the next one's going to be a little bit further down for a little. But you don't quite trust it. You still want to get an idea. You'll pick it up. And then you can be careful when you pull that thing around that you don't go too fast because it could come attached because, it's a big sail area that's on there. So that'd be an idea, something that's flexible that you might drop down for being able to do palletizing, but the precision isn't that problematic. But if you're taking something that's flexible like this, which might be like a piece of insulation that you're putting on the underbody of a Model 3 during a production ramp up, you might begin to discover you're having a hard time picking these things up reliably. I mean, just think about the problems that your printer has with all those paper jams, okay? It happens a lot. So manipulating these flexible items becomes difficult. Now you're trying to do the same thing on the shop floor and hope that never has a problem. Trust me, it will have a problem. And you're bringing it up and you're hoping it's not doing this business as you're trying to get it up there and fasten it. And that's the famous flufferbot problem that Elon had, and in which he realized that, wow, it doesn't work for flexible items. Now that's a simple flexible item. Wire harnessing is definitely something else, which is why we are seeing that on the end of the line, a lot of places that you need to have human operators going in there and doing it because no one's figured out how to automate that yet. It's definitely not with the current breed of industrial robots. That will be perfect for Optimus, but we still have a lot of production that has to be done with the traditional ones. And James has been pretty clear about it, is that a general purpose machine or robot will never be able to be better than one that's dedicated to a particular task. So those robots, they're not going anywhere. They don't have to worry about losing their jobs. A few here and there, because I think we've talked about some of them actually do nothing more than ferry a piece from the humans over to the robots. And we're saying, like, that robot's a middleman. Get him out. We don't need him. But those others that are actually there doing the work, yeah, they will probably stick around. And then, Optimus will probably be able to deliver the parts a bit more efficiently in a very different mode, because we don't have to worry about the same safety kind of requirements. But programming those things will be interesting, because you cannot program these robots in a vacuum, meaning that it's not like they're there just by themselves. They have to be aware of all the other robots around them. I mean, first they have to be aware, is the part there that I'm working on present or not? And if it is present, is it in the right position? And you go ahead and do it. And occasionally your work envelope may overlap with the work envelope of your neighboring robots. So you have to kind of coordinate those things and make sure you are doing it in a certain order. So that has to be synchronized, and that's something everyone has to worry about. So you have these higher level cell controllers that are basically like the conductor of the orchestra, that are making sure everyone is playing the notes exactly when they're supposed to play them, so everything goes well. But again, that's a certain degree of coordination, and you can see, people have to think this thing through. There's a structured logic that's going on. Can AI figure that out too? And the answer is, of course it could figure that thing out. I don't see why not.
Absolutely. And I mean, on the, even for those middleman type robots, I think that most of them, because they happen to be a reprogrammable robot that is, it's the same KUKA arm. You may change out the end of arm tooling, well, and then you'll just send it to one of the new factories that you're building, and it'll be reprogrammed. And instead of being a middleman robot, it'll become a welding robot, or something of that nature. And so they'll be able to preserve, all the ones that they've bought will get used somewhere, I'm sure.
Yes, and usually a lot of the times they end up in a community college somewhere. So you go there, and a lot of them, they have a lot of robot arms out there. The problem is they're about 10 years out of, old. So they're no longer using the factories, but rather than throwing away, they're going out there so that more and more students are able to get access to them and understand how they work and how they're programmed. So they will be repurposed. That's the whole idea of these robots, is they are very flexible and they can be repurposed to do different tasks. And the trick is the end of arm tooling. So if you go to any website for any of these manufacturers and you look at the arms, every one of them you'll see ends at what's the mounting plate, and there's like no end of arm tooling on there. Now they may show some examples like, oh, this is typically a spot welding robot, or it's an arc welding robot, and they might show an example of the end of arm tooling. But usually what they're showing you is just the naked manipulator. It's just there, and it's up to you to come up with end of arm tooling. And then you'll find out there are these other suppliers that you go to that actually specialize in the end of arm tooling for the robots. And then you're kind of shocked, and you find out, wait a minute, this end of arm tooling costs almost as much as the robot arm itself. What's going on here? It's like, well, it's because in many cases it's very bespoke, or we don't have the same volumes as these robot manufacturers have. So it can cost pretty much in the same order, sometimes more, depending on how sophisticated it is. And in many cases, the customer themselves are making it because they are the ones that understand the process. So when I was looking at what SpaceX was doing on Starship with the putting the fasteners on for the heat tiles, it looks like that end of arm tooling they probably either designed themselves, or they had to go out to some specialists that work in something like that. So that's unique end of arm tooling. It's not something they were just able to go down to the hardware store and buy. And more than likely that cost, just one of those probably cost more than the 3 robots that they had there. Once you get that design, then the rest of it, it's more or less intellectual property at that point. What's it supposed to look like? And then it's just going out and then building a couple of copies of it, putting in there. So you'll have that end of arm tooling, and then you've got the cell that it's working in. You've got to worry about the conveyor systems. You've got to worry about the fixtures and clamps that are coming in. All the sensors are going to be there. The PLCs, which are the programmable logic controllers that are the master ceremonies, you want to think about, or the conductor of the cell. You got to get all those things in there, and then the integrators you got to put in there. There's a lot of engineering that goes into absolutely one cell, and so if there's a way you can reduce their cost, of course, by repurposing, and that's typically what will happen, is that depending on how they calculate the capital, I mean, you can say, we've got a model, we're going to build a model, and we're going to like put all these robots in there, and at the end of the program, we're just going to like scrap the robots, and the next model is going to come in. Or you might say, no, why are we throwing these things out? Even though they depreciate everything else, we can still get a lot more use out of them. All I do is reprogram them. And typically that's what you do in many, many cases is find reuse, unless the robots really are having any, maintenance issues, or they don't have some sort of capability that you really need for that particular project going forward. But typically they will be around for a while. And it's the flexibility and the reprogramming that makes them useful. And again, it's the AI that's going to be the trick.
So as we move forward and the programming becomes easier and they become more aware, what's the next step in your mind as far as space, flame, and safety? I mean, is it something where it's probably a long time before we're able to eliminate some of the safety caging and get a higher density of robots and operations? Or does that take us a while to, or is that really
you can start to get there pretty quick, because a lot of the safety fencing you're putting around there is because you need operators that are operating close to where the cell is, because of loading and unloading of the parts. And once you're able to not do that, now there's going to be other safeties, as there's still going to be people walking through the factory, and you want to make sure they can't easily get access. The question is whether they become physical barriers or whether they become soft barriers. So if you think about it, if you go into some neighborhoods, they don't allow fencing, but people have pets and they've got to put down the invisible dog fence, something like that, to make sure that works. So, usually you make sure there's some sort of offset or distance. It'd be the same thing, is that rather than having these physical cages, you can start having a virtual cage, and that if someone moves into a particular area, you identify that, you shut down that cell immediately. And you just got to make sure the standoff distance is such that by the time it would take a person running at full stride, heading straight towards it, once they hit that, the robots are able to stop. Then you would be able to say, okay, we don't have to put any physical barriers in here. So that could happen a lot quicker, because now you don't actually have people who are needing to operate so closely. So rather than that being the rule, it's more the exception. You can start removing a lot of these things. So the safety cage will be able to go back. And there are committees that are working on things like that, of deciding that, and why the cages are set up the way they are, and why you have that offset distance. If you remember that the video of the operator in Shanghai, he accidentally tripped the light fence right there by getting in too close. He noticed there was quite a distance between that and where he had to drop it off. Because the theory comes down to, if he's sprinting and he decides to dive towards the robot, as soon as he breaks it, the robot's going to stop that quickly. I mean, that's how silly the standard is when you think about it. They're really thinking someone's that crazy or something like that could happen, because they have to look for that kind of situation. So
is it basically, I mean, they're basically planning to prevent suicide by, it almost takes that level of intention.
Oh, and there are operators that always figure out a way to defeat it, and they can't believe it. And really, it's a very, very intentional act, that they'll crawl in backwards through a conveyor that's running one way to kind of get into a cell that's operating, when they weren't trying to kill themselves. They just needed to get in and do something. They didn't feel like shutting the cell down to do it instead, so they find some other way. So they're always trying to figure out to make sure the system cannot be easily defeated, to not have anyone get in there. And we are already looking at these different standards, because there's the standard industrial robots, and then there's something known as a cobot. And a cobot means a collaborative robot. And a collaborative robot, in the sense, means that a robot that is collaborating with a human person. Well, it sounds kind of bad, collaborator. There's another type of collaboration where we talk about two robots working together on the same workpiece together. But the cobots, the idea is that they can't hurt a person. So you're working actually in close proximity. There's no safety fencing or anything else, but there is like a vision system. It's not like a light curtain or anything else. There's a vision system around there that's actually able to see where the robot is and see if there's a human. And if it appears like the human is within some work envelope, then it will do a couple of things to the robot, say, slow down. So these cobots are not really big. They tend to be a little bit smaller. They move slower. They don't have any corners. They're very soft and they're very compliant. So they can hit you, but they won't hurt you. But the problem with a cobot is because they can't hurt you, they can't go really, really fast in many cases, but they will have two modes of operation. They'll have like the chill mode when you're close to it. And then when you move away, then it can suddenly get assertive and can start going a little bit faster. So it'll do its operation. Then as soon as it sees a human is getting nearby, it's like, I'm going to slow down a little bit until it gets away. And then as the operator moves away, I can go back to full speed again. But again, if they hit you, you might get a little bit of bruise, but it's not going to be something that's going to be fatal or anything like that.
And so they also typically don't lift anything heavy, do they?
Yes. They're max. They're like 5 kilogram payload or 10. There's I think Fennec has one that's like a 30 kilogram cobot. And when I saw that, I'm like, you can't call it a cobot if it has a payload like that. It's already getting kind of strong. So now you can't do much. I mean, because when they talk about a payload of the robot, that's also the end of arm tooling. And you remember, it doesn't come with end of arm tooling. And so when you put a gripper on the end of it, you might already be putting 2 kilograms on there. So now you've got a payload that's down to 3 kilograms. So they're not picking up anything very, very big. So these are going to be light operations. And a lot of these are tabletop. I mean, they're really not huge. And some of them might be about the size of a human arm or just a little bit bigger. Whereas the industrial robots are like easily twice the size of a human robot arm and more. They get a lot bigger. So just one of the, so if you take like an industrial robot, typically one of the arms will be about 1 meter in length. So it's quite common. So you have like 1 meter here. So you've got about 2 meter reach, and some will be more. Some will have a 3 meter reach. So they're a lot bigger. And when you stand next to it, they're almost as tall as you. So you really get the impression like, yep, that's big. But the cobots are more human scale and much softer. And they're actually designed with the motors that they're compliant. So as you probably know, with a lot of mechanical mechanisms, that if you stop the motor and you try pushing on it, it doesn't move. It's just locked in place because of the way the gearing and everything is. With a cobot, if it stops and you push on it, it'll move out of the way. And that's one of the regulations that you have for a cobot, is that if you push on it, it gets out of the way. And part of the reason is that industrial robot fatalities are very, very rare. I mean, there were some in the early days where people were struck by it moving a bit quickly. But the last 2 fatalities did not have to do with being struck hard by the robot, but by being accidentally pinned by it. So an operator got behind a robot, I think it was about 10 years ago, and the robot was moving back. And then the e-stop went because the robot had sensed that, there was something wrong, and it went whoop back. Oh, I got to stop, because I thought it was hitting something. The problem was pinning a person back there, and they couldn't get the robot out in time before the person suffocated. So that's why the cobots are set up that if it somehow pins you, you're going to be able to push it out of the way without any problem.
Gotcha. That's an area I don't have any experience with yet, but I think is fascinating because it's definitely, a lot of the challenges of automation really are front and center in cobots. That as far as the programming, like it's a different way that you have the ability to program cobots, and then the human robot interface is a very interesting challenge as well.
Yes.
And that's going to be really the space that Optimus plays in primarily because in pretty much every way Optimus will have to be able to operate as a cobot. And that's fascinating to think about, and it certainly, I mean, it seems like the design criteria so far all fit with that you'll be able to overpower the robot. It should be able to see and respond to you and not, be operating at speeds or, moving in a way that is dangerous to a human while a human is nearby.
Exactly, exactly. And the way robots are traditionally programmed is using something called a teach pendant. And you just think of it as like a joystick controller or a gaming system where you are using these buttons to drive the robot to a particular position. So you're activating, putting everything over, and then you're looking very closely whether it's getting down to where you like it. And if you like the location, you say store location. Then you'll add some other instructions in there. You might say, I want you to delay right here. I want you to turn something on. So maybe it's a welding operation. Say, okay, turn my welding torch on here now. And then you're going to start moving it along and then store another location. You're going to say, oh, by the way, when you move between those points, I want you to move with this speed. And I want it to be a straight line move. Make sure it's straight line. It's not wiggly or doing anything weird. That has to be a straight line. So you would say the type of move, the speed of the move, and then maybe there's a little delay at the start to make sure the arc gets started, and then you go along, and at the end maybe you have a little bit of delay, and then you turn the arc off, and then you move away and retract. But all that you're doing with this little controller. And everyone's kept on thinking, there's going to be an easier way to do that, much easier way. So the analogy would be, it's like if I'm pushing on buttons and suddenly you see my mic is moving around because I'm pushing on some buttons. Well, the other way that everyone wants is they want you to just be able to grab the end of the arm and move it like this. So and that's what the Cobots started to do, is they allowed you to actually be able to grab the end of the arm and say, just take it and go right down there, because they wanted to eliminate the teach pendant, because they thought that would make the programming of the robot easier. I'm like, well, it's a different interface. It didn't necessarily make it any easier. And then what I've been doing for about 40 years is we've been doing something called robot offline programming. And we've had to create a virtual world. So there were all these schemes in the 1980s, like what are the best ways to be able to program the robots, and short of actually being on the shop floor. Because when you're down the shop floor with the robots actually there, which is a logical place to program it, the production line is not running. And if it takes you a couple of weeks to reprogram the robots, that means the production line is down for that time. So you're trying to figure out, well, how can we do this offline, off somewhere else? And once we teach that robot that program, we could just transfer it to it, right? That's all we have to do. Just take the program, put it on down, and put it in there. The thing is, you have to have an identical environment to be able to go in there to make sure you understand the movements. Is it colliding with anything? Is it interfering with another robot? Is it position right? Everything else. And in some cases, they were trying to set up these rooms that they'd almost have like Legos they'd put together to simulate what that environment would be to get it to work. I was like, that's a bit hard. And our idea was to do it virtually. So you create a virtual 3D world based on the CAD data that you have, and you operate in there. And I could show you an example of that, and maybe you could be able to visualize an idea of that. So I will try to bring something up here and do a quick present of the screen, and then we're probably going to end up all of us going all over the place here. Let me just go ahead and see the entire screen, and we're going to be right there. And I'll share, and I'm going to go ahead and bring something in just a second. There we go. Okay, can you see this, Hans?
Yep, it's there.
Okay, so this would be like an example of a spot welding cell. And you see, it's not the real cell. It is a virtual representation of the cell. And what's going on here is that we have a car body that's going to roll on down here. You see the robots are sitting there waiting. They're in what's called a wait state. They're waiting for a signal to go ahead and start moving. And that one of them is actually sort of a pick and place robot, where it's going to pick apart from the stack over here, put it in place, hold it in place, and then the robots have to come in and weld it into position. So clearly that all has to be coordinated. We have to make sure the robots don't bump into each other, and it just keeps on repeating that cycle again and again and again. Now, there's a lot of engineering that goes on here. The first thing, of course, is where's the placement of the robots? Where do we have to make sure the robots are placed so that when the car body comes in, the car body doesn't collide with them? Second, we have to make sure that the robots are placed, the placement is not only to not hit the car body, but it can reach all the points that are assigned to that particular robot. So you need to make sure that's there, and that placement can be a couple of items. One, where is it on the floor, and how high is it up in the floor? So these pedestals that they're on, you might need to engineer them to be of a particular height. And as you can see, this robot is really up on a pedestal to be able to make sure it's able to reach that. At the same time, you have some custom tooling, like what you would have here for this gripper, to be able to hold the panel that you're going to be putting on in there. And then, of course, there's the coordination of the movements of all these robots to do it. And then there's some selection criteria, because I think these might all be the same robot, but they don't necessarily have to be the same one. So these robots come in different sizes. So you may need one with a slightly longer upper or lower arm, or you might even have these shelf-mounted robots that are hanging upside down versus ones that are going to be floor-mounted or on a pedestal. So you can get that selection criteria, and then you need to look at your end-of-arm tooling and know that, well, we're working in pretty close. Let's make sure they're not bumping into each other. And what's the end-of-arm tooling going to look like? Now, the step that you go from there is that you have to look at each robot, and they're going to have their own programs. So what typically does a robot program look like? Let's go ahead and see if I can bring one of them up here. Is so the robot will have a series of moves here. And so these are the statements. So this is a type of move which they call the PTP, which is the fastest, easiest move for a robot, where it just goes from one location in space to the other, and the trajectory of the arm cannot be described as like a straight line or anything like that. So it just goes straight to that point. And then you will go ahead and then maybe start doing a bunch of moves which are linear, which are going to be going on down there, and you will have different speeds. So maybe 100% speed, a little bit faster speed to get in there quicker. And then you're going to call a program called Spot. And pretty much what Spot does is it sets an output signal to say, okay, turn the spot weld gun on. So it's basically flipping a switch. And then it's waiting right here. This little green dot right here tells us that it's waiting for that command to stop. So it's sending an instruction to say, do your welding, and now wait for it to be done. And when it's done, let me know, and then I will release. And then I know I can move on to the next point, the next point, the next point. And then you might have like some main program that you just keep iterating through, where you're waiting for a synchronization signal that's coming from the others. So the signals are very, very simple. And from this, well, let's say the statements are very simple. And from this, you see we have a program for each of these robots. Now, all we need to do is take these programs, especially these things here, and transfer them to the actual robot. Now, this is in a generic language. Each controller has their own specific language. All we have to do is translate that. So we take these instructions and we convert them directly into the KUKA specific language instructions to execute a PTP. And in some cases, we might have like a delay statement, or like we saw, like a simple signal that you're sending out. You're turning a switch on, or you're waiting for something to come on. That's a very simple kind of instruction, which has no three-dimensional information in there. And then there's the others where the instruction is, I want you to move with this particular speed using a particular tool point offset, going to a particular location in space. And that's where you now have to calculate where is the Cartesian location of this robot. And I think I would be able to sort of show, if we get some robot positions. Aha. So we've got some locations out here in space, which are examples of where the robot can go. So you can see that's one position for the robot here. And if I click on this, that's another one. So I can get my robot to move around and show me where that is. And if I don't like the location, I can then go in and edit that location very easily. So I go in and say, I would like to take the point and just move it over to here instead. Or in that, I can also say, instead of doing it that way, let's take the robot and move it itself so I can see what it's like when it moves around. And you store that location, and now that's something that you have to send down to the robot controller. And that's done with a simple post processor. Take it from the simulation we have here to the actual floor. So if we can see it's working here, if we're happy with the results that we're seeing, push a button, the actual robot's able to move. Now we do not have to worry about taking up the robots on the shop floor. As a matter of fact, we can program these robots before this cell is even set up. In the old days, you had to wait for the cell to be set up, and then when it's set up, you could go in and program it. Now we can program it in advance, and when you go down there, all you're doing is you are calibrating it, or you're kind of dialing it in, because there's always going to be a difference between the ideal positions of these robots in the actual positions. But they're pretty minor, especially in this day and age, because with CAD programming, they can get everything pretty close to where you want it to be. In the old days, the position of the robots was more of a suggestion than anything else. And you get down there, you'd be surprised how many inches the robot was actually from the location that you thought it was. And you had to kind of go in and touch up the programs quite a bit. But now they're dialed in so well that You push the button, it goes down to the real robot on the shop floor, and it's done. But I have to sit here as a human being and create these programs. I have to kind of look at that and understand the positions. Now, the positions of these points are not random. There is going to be an engineering drawing that's going to tell me the positions of the spot welds on here, because some engineers have analyzed this car body and say, this is where the spot welds need to be. This is the spacing of them, this is the position of them, and different welds will have different characteristics of how they're welded, depending on whether it's like two pieces of sheet metal coming together or three pieces of sheet metal. So you're going to have a certain amount of current that has to go through, a certain amount of pressure that you're going to be applying on the tips, and the amount of time that's going to be needed to do that. So that information is in there, and something you would also put into your robot program to make sure the process is done correctly. There are some other points where maybe you're more free to choose, like your air points. How do I move from one location to another? So how do I get in? How do I get out? What's the quickest way? And then, of course, you're looking at the cycle time to make sure you can hit all the points that you're allocated in the right amount of time. And if you can't, you're going to have to go in and figure out, what do I have to do? Can I change the order of operations of the welds? Well, maybe you can, maybe you cannot, because sometimes you have to hit certain welds in a certain order, and then you can come back and do others. Just as we know, when you put a tire on, you're supposed to use the star pattern when tying it down, so or bolting it in, rather than just going around, which might seem like the most efficient way. So all this information has to be considered when you're creating the program. But still, that's something an AI could do. All it has to be able to do is understand this three-dimensional world. It also has to understand, how do I get access to the engineering drawings and open up the engineering drawings to find out where those weld spots are. And now typically what ends up happening, if we have to do, usually our customers are doing this project, but in some cases we might do it for them. They will come to us with an Excel spreadsheet of all the locations of all the points. And it might be 3,000 points out there. And they'll say, oh, don't worry, we've already allocated it. And this is going to be robot R1, R2, R3, R4. In R1, we've allocated these points in the spreadsheet. You go ahead and take those points. And those are the ones you have to worry about. So we kind of know which ones we are dealing with, and we're able to pull that information out. Because someone somewhere else was looking at the whole process and made that decision for us. We did not have to do it. But you could imagine, well, wait a minute. Why do we have to have that person making the decision? Why can't I just have all the welds? And why can't I just look at it, especially if I know what all the stations are doing? The station before me, the station after, what's the quality of the welds, what's the importance of the welds? Can I change the allocation? And if I change the allocation, am I going to be able to improve the throughput? So that's something that's very hard to manage. In many cases, they just sort of decide certain rules of thumb that this is how we work, because we always are able to produce cars this way. As much as we like to fine tune it, at the end of the day, if we're not getting cars off the end of the line, we're losing money. So having an AI be able to do that and know where all the information is, and be able to access that information and not have the guesswork, be able to pull it up, that would just be a push of a button. So I could see down the road, you would have an AI that is in effect taking this software program and driving it and creating it, and then downloading it to the actual robots. So there's no reason why that could not be done. So does that help? Point out
that's very
the one way. Yes. So the visualization now has to go like, this is not your typical large language model, because it's a bit more than just saying, oh, I want to create a bunch of statements here, like I would in Python.
Mm-hmm.
You have to understand these statements have a little bit more information behind them, that as I go through them and I pick any one of them, it's going to show me, well, it's that position in space, and you have to understand something about that position in space. And you have to also understand the type of point it is. Is it an air point or is it a weld point? What's the process you're doing? And so that could not just be for spot welding, it could also be for arc welding, it could be for sealing, for painting, anything else. And creating these programs can take an operator several days or a week of programming time to do what seems like, well, wait a minute, it's maybe a little bit more than a dozen points. Why does it take that long?
Is that a day or a week for one of the arms, or is that a day to a week for this cell and coordinating all of them together?
Could be for an arm. So in the old days, it could take a programmer on the shop floor you would have one programmer per arm, and you might have 6 to 8 arms in that cell. And so there would be other people programming the other arms at the same time, and they would be sort of saying, okay, we've got to make sure that you understand that, you know, at this point we're getting the signal, or you may have some overlap. So in many cases, you've got to make sure, wait a minute, when you get to a certain area, you have to wait until I've exited. So you might have to have some coordination, or you may know ahead of time, oh, the robots, they may come close, but they're never going to collide, don't worry. But as you try to put more and more robots in there, naturally their spaces are going to overlap. So you have to be able to do that kind of coordination. So a lot of times that is what takes the time, and the fact that I had to keep on testing and retesting the programs, going through, verifying that everything is working all right, and their cycle time might not be quite right. And then, you know, eventually they would actually start executing the program. So at first you're putting it up there on a normal car body and you're not welding anything. It's just sitting there and you're just using it as reference. Well, at some point we're going to start doing these welds. And then you start saying, quality of the welds is not quite so good. Well, bring in the next car body. Let's try it again. So, and obviously you don't want to cycle through too many car bodies. They're going to end up being scrap. You want to make sure that you do as good a job as possible. So you try to get your programs right ahead of time. And then at some point, you know, rubber meets the road, you just start doing it. You're going to start making some mistakes. You're going to start fixing that. You might have some arms crashing. You're going to have to fix your end of arm tooling. So it can be very tedious, and going through these steps can also take a while. So that's if you've got a human operator in there. If you start developing programming macros, which is also something we've done a lot of times, you just push a button and we can generate all those points for you. And then you would just go through and validate that the program is working right. So you would, you know, give it the oversight. And, you know, we have some examples. When I was first programming some arc welding robots, and this was back in late 80s, early 90s, a project for Caterpillar. Their rule of thumb at that time is that for every hour of cycle time of the robot, they would need from 50 to 100 hours to program it online. Now, these spot welding robots typically have a cycle time of about 45 seconds. Caterpillar welding cells will have a cycle time, minimum cycle time of maybe 45 minutes. It could be a lot more, because their heavy deposition and arc welding is a very slow process, and they have a lot of welding that they have to do, and their parts are very, very big. So you're looking at robots that might have several hours of cycle time. And so already you're looking at, oh, so that's a couple hundred hours of programming time. And then you start breaking that down. So, well, wait a minute, you know, that could be several weeks, 4 to 6 weeks to program that robot to run that particular job. If you're only then doing about 100 parts, you're like, oh my goodness, you know, it's like, that's all we're doing. And then that robot has to be programmed for the next batch or the next one. So then you begin to realize that 50% of the time your robot is in school rather than actually doing work. And the only way to cut that down is to bring it offline. And in that first project, we basically mimicked exactly what the robot was doing on the shop floor in the software, which meant it took us almost as long in the virtual world as it did on the shop floor. So rather than someone staring at the real part, they were doing it in here. But then eventually we figured out, you know, we can be clever about this because we know so much about our environment. We can start having macros that you just kind of select what looks like a weld seam and automatically generate the points along that seam. And start doing the approaches, because the approaches are done almost the same way, start getting more and more information. Now we're at the point that we can generate these programs at a fraction of the cycle time. So the first goal was to try to create a program at the same time as the cycle time. So if it took 1 hour to run the shop floor, we want to be able to program it in 1 hour. Now we can do that same program in under a minute, because we understand it enough. And we've done that with programming macros, not with artificial intelligence, but by creating really, really good programming macros. So we can see that you can leverage the advantage of a virtual world to make the robots on the shop floor be programmed much more efficiently. But still, you do have someone there that's kind of specialized to a particular application. So, you know, we focused a lot on arc welding. We've also focused on some other processes like plasma cutting, deburring, some finishing type of operations and painting operations. These macros to be able to do it, but there's no reason why the AI couldn't come in and eventually start doing that and coming up with better and better ways of doing it. So that's been my task from like the past 40 years to figure out how to make that easier and easier. And right now we're doing it with a virtual world. So that's it. That's the intermediate step, is that you have to bring it in, create this virtual world, program the robots in the virtual world, the real robots will work. Ideally, it would be nice to just put the workpiece in front of the robot. Here's your workpiece. Have it look at that. Say, oh, I know exactly what you want me to do. And just program it that way. No, get rid of the virtual world. There's no reason. So that's something the AI can do. And I think I've told this story a few times. Part of the reason I want to do it is I see it as like a bookend of my career. Is that when we first started my first company, Deneb, we visited one of the professors at Cornell. His name is John Hopcroft, and he was definitely a legend in the area of computer science and compiler theory and a lot of other algorithms. And he was just starting to work with the idea of robot programs and what was like one of, I guess, the AI summers before the next AI winter was going to come along. And there was a lot of thought that you could use AI to program the robots. And we were taking like this more very traditional approach that we were just going to program the robots in a virtual world almost the same way you do in the real world, without a whole lot of intelligence. It's just that you didn't need the real robot to do it. He was already thinking of like, well, I want to be able to put an assembly of parts down the table, have a robot look at it and figure out how to put it together without telling it anything else. It's just like, just examine. It's like, oh, this is what you want me to do. and we thought, wow, you could do that. And this is 1985. And I said, well, he must have some trick up his sleeve or some idea he's thinking about. But, that was he believed it could be done. And then I think the reality set in that it was a much harder problem. And so that never happened. But it's been something that's been nagging me, that entire time. I was like, well, why can't we do it? Because he's kind of right. From first principles, we know in many cases, if you come in with someone is well educated and you put a pile of parts in front of them, they can figure out how to put them together or what the processes are. So why can't a piece of automation do that as well? So it was a far-fetched idea at that time, but now I don't think it is anymore. So I really think we're very close to that stage that you start bringing in what it is you want to do and you just show it to a robot, and it doesn't have to be Optimus. It could be any kind of traditional industrial robot. We'll look at it and say, this is what you want me to do.
Mm-hmm. So what do you think of David's question here? How long does it take to get an ROI on an investment into a station like the spot welding station that you just showed us?
Okay, so on the spot welding, when they're doing an ROI on that, they're costing it over the entire program. So, they might be looking at like a 3 to 5 year kind of program that they're doing. And the expectation is that all the CapEx that goes in there is going to be recovered over that time. So that's not going to be really, really short. But I have seen situations where people have looked to automate something and they really weren't sure, whether it was going to be worthwhile, and they started doing it. And in many cases, it could have been as short as 6 months. But typically it's going to be in the order of 1 to 3 years, especially for hard automation, because there's a lot of investment that goes in there. From the standpoint of people using our software, a lot of times they're able to understand something that's going on in the cell and then get immediate cost savings that they almost pay for the software in a matter of a couple of months. But that's very different. But the ROI, typically could be a couple of years because they're spending a lot. They are definitely spending a lot of money. It's not going to be a matter of months. So you do have to look out over the period. And if in some cases, you may have to think about future products as well. So I've got something that's going to help me for this particular project, but it's a very small batch and it's only a 6 month run. However, I know there's going to be another project right after that and after that and after that, that I'll be able to continue to use this cell again and again for those. And then I'll be able to, kind of depreciate it against the cost of those particular projects. But it will require a little bit of reprogramming.
And then one of the other questions that I was wondering is, how I'm sure that in some of these evolutions of creating these programs over time, there have been attempts to basically use a human to remote operate the
Mhm.
arm and kind of record that as a macro. How does that kind of play into all of what you've shown us so far today?
Okay, so
I mean, is that basically what a
usually,
teach pendant is, or is it?
well, the teach pendant is local. So the original teach pendants it was a box about this big that would have a bunch of buttons on it. They might have a joystick, a safety button on there, and they had an umbilical that was connected directly to the robot controller. It was really long. So it was like a vacuum cleaner. It got to be kind of annoying that you're going around suddenly, oh, wait a minute, what's this? Something's a snag. You kind of move it around. And part of the reason is like just the safety feature of that, the fact that nothing can go wrong with wireless transmission. And the let's say the RF noise, the RFI inside of a factory can be pretty bad. So anytime you're trying to do something wirelessly, it just because you get people there with their arc welding and the RFI it puts out. But there are now teach pendants that are set up that can be wireless. That'll be more like just an iPad that you go in there and you push different buttons and you'll be able to move it around. So that's typically what the interface is. And there's no reason why that couldn't be done more remotely. The only reason it's not is that you're going to be able to see what's going on. So usually the operator is actually right there. Now, it doesn't mean there aren't examples of teleoperation that are going on or programming that has been done remotely. So for example, I have programmed robots that are several hundred or thousand miles away from me, just because I have a virtual layout. I've created the cell that I sent it to someone who's local, puts it in there, runs it, and it's like, oh, it's great. Just had to touch up 1 or 2 points, or everything was fine. And that's because the virtual world and the real world we had was close enough that I was able to program it that way. But I wasn't doing it tele-robotically. Wasn't actually seeing it. Now, there are definitely examples, and I know there have been some examples of like robot surgery and other things where operators are able to do that because they have the cameras and everything set up for that. And there is a company in San Antonio called Plus One Robotics, which kind of does something like that. So they're working these robots that are in packaging and doing sorting of patches coming off conveyor lines, where the robots have to go and pick up these packages that are coming in random positions and orientation, and they're random packages. So whatever the material is, they're made out, it's gonna be different, the size and everything else. So they're picking these things up, and they have to figure out really quickly, it's gonna go here or there, or just sorting around. So it's doing pretty much what you would do in a mail sorting room, where a person is doing that, now the robot's doing it. And there's a vision system connected to the robot, and it does a really good job. And it's right 99.9% of the time. And we know what the March of Nines is all about. It's like, well, that's really great, 99.9, but that means like 1 in 1,000, it has a problem, right? It looks at something and it can't figure out what's going on. And it kind of freezes, like, I don't know what to do. What should I do? Well, in that case, a signal goes to an operator who is hundreds or thousands of miles away and says, hey, this robot over here has a problem. Just like Waymo and Cruise do. And suddenly they jump over there and they've got a vision system that can look down what's going on. And they kind of go over and point at something, tell the robot, that one, go get that one, goes and gets it, and then kind of continues on its way until it has a problem. So you've got someone sitting in a nerve center that's managing hundreds of robots around the world, and whenever there's a problem, is able to go in there. And that's why it's called Plus One, is that you've got a person that's able to jump in whenever they need to telerobotically help out. And again, think about what's going on there. It's an awful lot like a CAPTCHA. That the whole idea of CAPTCHA, you're trying to teach an AI. So every time the robot fails, human operator goes in and says, but the advantage is that person does not have to be local. And that person is able to manage a lot of them, so you get the advantage of it being kind of parallel. And so you're going to see more and more operations like that, where there is teleoperation of the robots, but in a very minor sense. But when you're creating a big program, a lot of times you really have to be very close. Or I think you'll see more and more of this AR, VR kind of situation, where you'll be able to jump in and with a pair of VR headsets, go in and study exactly what's going on as if you were there. And that would be cool. And part of the reason that will be cool is that in many cases, you cannot go into a robot cell when it's operating. No, it's not a good idea, but it would be really awesome to be able to go into a robot cell when it's operating and not worry about getting hit. And that's something you'll be able to do in kind of like an AR, VR kind of situation.
Yeah, it's interesting because, just by outfitting those with cameras currently, if someone at Tesla was interested in doing this, that they could do a post event, reconstruction of an entire sequence in a cell
Yes,
from nerfs, just like they're doing right now for cars and intersections. And you could see all of the interactions, and being a nerf, you could travel around the scene and look at it from any perspective that you'd like. Basically do a full AR or VR reconstruction of that event. So
yep,
yeah, and that's the thing, that they are developing a lot of these tools, and it'll be interesting to see what we get to be privy to on the outside. We know that there's a lot of interesting, smart, creative people who are unleashed on problems of all varieties inside the company, and so they're going to be, using whatever it is that it's available to them, and these are going to be some of those tools. And so, yeah, we know that they're going to be using them in interesting ways, but it's interesting to speculate on what those might be, since we probably won't actually be able to, you know, see or discern what those things are from outside the company. At least not in real time. We'll find out well after the fact what happened.
yeah. If you get enough log files of what's going on, and that information is out there, you can easily reconstruct a situation where you may have had a problem with a part or some sort of failure. So it becomes like a CSI.
Mm-hmm.
And now you can go in and you can play it in slow motion. You can look at it from any angle. You can freeze frame and look at it from the top to bottom, understand everything that's going on. And then you say, all right, now we understand what the problem is, and now we can come up with a solution. And then you propose a solution, and then can play to the same situation. So a lot of what you're seeing happening with FSD, of looking at various scenarios and intersections and being able to simulate a variety of different things, you can do the same thing in a robot cell. And in many ways, we're already doing things like that in the robot cells, through the simulation. So when I've seen everything that's been going on in FSD, it's been very familiar territory with me, because
Mm-hmm.
yeah, I've seen that movie already. We were thinking along the same lines, but obviously it's a different problem. But there's enough similarities that I can see the overlap. And then what they learn from FSD and what they then learn from the programming of Optimus, you start to bring that back to the traditional industrial robot cell, and you're moving a lot closer to that alien dreadnought, without a
Mm-hmm.
doubt. And again, then you can start thinking about stacking these things, right? Because a lot of that wasted space is all above you. And of course, you can make it a little bit more compressed in the floor, and then you can just start bringing more and more of these robots closer together in those cells.
Mm-hmm.
So it will look very different. And then the interesting thing will be seeing a very intelligent agent that's going through trying to optimize the shop floor, will start proposing different industrial robot arms than the
Mm-hmm.
ones that we already see. Because I might
Yeah,
say, well,
that
wait a minute, we actually need one that's kind of this size or this configuration. This is the ideal kind of candidate. Because right now we're limited to our selections. It's like, that's not necessarily the optimal one. That's what's available in the catalog.
Mm-hmm.
Now, the
Or that's the
catalog was
one that
built
we
up over
have.
years of experience, yes, and because a lot of people have thought about it and are trying to come up with what they believe are going to be the best suited robots for a lot of these different applications. But it doesn't mean there isn't always another or new application or a new size robot or new configuration you can come up with. So I see that happening as well.
One of the things, while you were talking earlier about, just how long it takes a person to create that, like, I only imagine that in on the shop floor, a lot of times what ends up happening is that they get a program that is good enough to meet their objectives, and as soon as it's good enough, they move on to the next thing. And this is probably the rule, not the exception. And so there's probably a lot of room for optimization to improve cycle times, and just wherever the bottleneck is. And obviously that's a huge opportunity for some sort of um, AI powered optimization algorithm to
Mm-hmm.
go through and do those types of things. But so, trying to think what the best question is there. It seems like with Optimus, one of the things that will be possible in the not too distant future is, if they can get Optimus to control itself, then they could outfit these one-armed, Fennec type robots with the ability to articulate themselves in space autonomously, that you could, because a lot of what you're talking about is just trying to coordinate how the thing moves to get itself into position. Like there's basically three things that are going on. There is getting into position, then there is performing the value added task,
Mhm.
and then there's getting out of position so that the work piece can clear the area. And of all of that, I don't, different operations are going to be different as far as how the time breaks down between value added and just moving, conveying the work, the tooling to the place that it needs to be. But all of that movement, moving into and out of position, should be something that I would think could be handled by the robot itself. Once Optimus knows how to control itself, well, these robots should know how to control themselves. And then it's just a matter of teaching the whatever, if it's a spot welding robot, okay, you need an algorithm to understand how to spot weld, and then I can just give you, all of the, and there are so many things that you could learn about spot welding. You can feed it information, you have this many layers of material, these are the materials that they're supposed to be, so you should apply 100
Mhm.
psi worth of pressure, and you should run 100 amps through there. Well, yeah, that's what it's supposed to be, but this is manufacturing, and so this piece is a little bit too big, that piece is a little bit too small, the material properties aren't exactly right, and there's actually feedback that each of those things can get, and so they can learn how to actually achieve better quality spot welds through a neural network. And so I think that it seems like that would be the direction that all of these things head, that you've got one thing that's for conveyance, and then you actually just over the course of manufacturing teach these, they'll start out as general, I'm going to teach it this weld for this car, and then you eventually build that up into, I am now a welding algorithm that
Mhm.
knows how to achieve any number of different types of welds in any number of different types of positions,
Exactly.
whatever that this end of arm tooling is capable of, because there's a bazillion different types of welding processes, materials, the complexity in just welding, and that's only one of the complex operations that happens in a factory, is very that's an endless well.
Yeah, and a lot of it is the design of the tooling is like one size does not fit all of the spot weld guns. So you'd like to have as small and compact a gun as possible, so you don't have to have a robot that has to have a heavy payload, and you don't want something that's too bulky. But sometimes, depending upon the location of that weld, you may have no choice but to have this really huge one. And you will see some in the underbodies and some other places that come in there where the gun is just ginormous, and it's only to hit just a couple of welds. And you're thinking there, it's like, couldn't they have designed that thing somehow different so it's easier to get access to that weld? And then we saw the welds at the top that were going over there. Those are very easily accessible, so you can hit them with a normal kind of spot welding gun. But remember, the spot welding gun also has the utilities that are going to get to it. So you have these cables that are around there, and there's all these things you got to think about depending on how you're going around. Is that if I start in one location and start coming around like this, my wrist is going to wrap up, right? Well, I've got the cabling on there, and that cabling is also going to wrap up, and I've got to make sure it doesn't get in the way and it doesn't snag at anything. And then when I'm done with that weld or with that process, and I get out of the way, I have to come back, and I can't start from where I am. I'm going to maybe have to unwind myself. So that's one of the things you have to think about. And when you do that unwinding, you got this big gun that's going around, you're kind of worried about whether it's going to hit anything. So in many cases, most of the time is spent figuring out how to do all your air moves, how do your setups and everything else. The process in many cases is very simple, it's hitting the points. So it's getting to the points that are very hard. And then sometimes when you're applying it, especially if you have a continuous process like a sealing process or something, you're going around everything that's all right, and then you come in a particular corner And you got to get around that corner really fast. The problem is the robot slows down. And I can't do that because, when you get a cocking gun and you start pulling in the cocking gun, you better pull that cock at a certain speed. If you change it, then suddenly your bead is going to get bigger or smaller. So you've got to keep that thing right. And the problem is that you're looking at it and say, well, wait a minute, it's just like this short little move. Why can't the robot do it? It says, well, because you're looking at it at the tip. What you have to do is you have to look at it out here at the wrist. And the robot is like pointed in this direction. And to make it around there, suddenly the wrist has to move a long ways because you've got this very long arm. And the reason you have this long arm is because it's in the underbody and some weird place. And it's the only way you can get up there. And now you're trying to go around there and expecting the arm to be able to do all these things. So there ends up being all this complexity to be able to figure it out. And then you're right about the process control, is that you want to build up this knowledge base of what is the type of weld that I'm doing, what's the process I need to apply there. And there's definitely quite a knowledge base you need to have for spot welding. The type of material you're going to have, the thickness of the material, the how many sheets are stacked up at that particular point. And then there's arc welding, and boy, that is just something else. I mean, the database you need for that to be able to identify what's going to be the right process parameters. So it's not as easy as saying position my torch here and just drag it on over to there. And the angle that you have, there can be it's an art to figure out just what that angle is supposed to be, whether you're supposed to be right in the bisector or not.
It's rarely ever even static. Usually you're weaving it up and down, or
you could be weaving. It'll depend. And so if you're doing like heavy deposition, you need to do the weaving. Sometimes the only reason you're doing the weave is so you can do the seam sensing. So typically weaving is for heavy deposition, but you could do a thin weld, and the reason you're doing that is how the robot is able to find its way through. Now, we talk about camera systems and everything. They've tried for years to put camera systems in arc welding, and they don't work. You know why they don't work?
Probably
the camera gets blinded for the same reason you get a welder. Well, the arc is just so bright they can't see anything. And so a lot of times the camera systems have to look ahead of the weld a little bit, or they've used like these laser trackers to try to do it. And then the problem with the laser trackers is it fixes you into the orientation you have for your gun, which means you can't roll around the wire, which sometimes is what you need to do. So it creates another host of situations. But the clever way they have is by doing a weaving, it's almost like closing your eyes and feeling your fingers hitting tops and bottoms of these surfaces. I can kind of tell where I am in there. And just by feeling that, I know where my next step is going to be. And it does it through the change in voltage. As it's going in between that little bit of gap, it's able to sense the fluctuation in the voltage, and it knows exactly where that seam is, and it will then correct. And it's amazing. And this is done, I mean, it's probably done just by some very clever engineers in the 70s and 80s that figured this things out. Double E's that know something about applying filters and everything else, and some sort of weird feedback loops. It's just amazing. So that still works, and it's still used today in many cases. And that's why you need to do that kind of welding. It's not necessarily that it gives you this nice appearance. And of course, that's the other reason you want to do arc welding as much as you can. Even if you have small batch, the quality will always be the same. So the problem with manual welding is, depending on who the welder was that particular day, you may or may not get a good weld. And once you automate it, you're guaranteed it's going to be a good weld. And again, that's the reason why SpaceX is moving that direction, is that even if, they're not making, well, maybe they'll make millions someday, but, even with the small numbers they have there, it makes sense to use as much welding automation where they can. Rings, it makes sense because you don't need necessarily a robot for that. That could be a welding machine to be able to make a ring. But when you have more complicated welds that are more random in their position orientation, then you need to have a welding robot to be able to do that.
So just out of curiosity, and I doubt that the viewers will know or care what this is, but have you done much work with submerged arc welders, or are you doing mostly open arc?
Yeah, I mean, basically all of them. So MIG and TIG, submersed, typically those are like the welding machines where you're trying to weld two things like aluminum together. And the problem with aluminum is it reacts really well with oxygen. So you need to make sure that you keep the oxygen away from the weld you're going in there. And it can also be the same thing depending on the kinds of iron materials you're putting together and what those alloys are going to be. And you can do submersive a couple ways. Usually it's with argon would be one example, or even CO2 if you want to put in there. So you could those are basically shielding gases. I should say that. So
Yeah.
pretty much the argon displaces the oxygen long enough that you can do the welding without the oxygen getting in there. The submersion is that you pretty much are putting it underneath like a type of sand. So basically you cover it with the sand and the arc is going underneath it. And then you've got something that's depositing the sand in front of the arc. And then you've got a vacuum cleaner right behind it that's sucking it back up as you're going along. And typically those are like long straight welds that I've seen those like welding machines when, you go out to a shipyard and you need like a really big piece of metal for the side of your hull, right? Long straight piece. And you just imagine, it just kind of comes right out of the steel mill, right? It's like, no, it comes in smaller sections.
Yeah.
And now what you have to do is you have to take those smaller sections and you have to put them together. So it's like getting sheets of paper and then having to get Scotch tape and put it together to make a really long, big piece of paper. And those are just very flat. So you can put them down on a welding machine that just goes down and just does a straight move along there. And in some cases, those might be an example that you might use submersive welding if you want to make sure you're not getting any oxygen to go in there, because that could affect porosity and the underlying properties of the material.
Yeah. That's. I'm not a materials joining engineer, but I went to a school where we had a materials joining program, and so I knew a lot of MJs, and their world seemed very interesting. A lot of challenges.
It's extremely interesting in what they have to do, in that arc welding is still kind of an art. They're trying to make it into a science, but it's pretty hard. They get better ideas of how it works, but still in many cases, you just have people that pick up experience, years and years of experience, and they know what to do in certain situations. And the problem is transferring that knowledge. And a lot of people who are very good at this profession are retiring, and not that many people are filling in the back ranks. So it's like now is when we need to start getting, the information from a lot of these experts and putting them into what we would call these expert systems or knowledge-based systems, which will be AI, to make sure that when we go out and we try to do the welding, we're going to get the same quality weld. But it's a hat tip to anyone who does welding and really knows what they're doing on. It's just, I've been around enough of it, in shipyards and heavy equipment to see what's going on, and kind of the smell of the it's not hopefully burnt hair doesn't smell quite that bad. You kind of get the idea of what's like the sea stuff is being built, and you just kind of appreciate it when you look at what goes into it.
The number of variables that are at play in materials joining are just incredible, from not only the process itself, but then the material properties and
you have these huge trade-offs that a lot of times when they want to make an arc welding cell, they have a lot of different welds that are going on in there. And in some cases, they need to use a different type of wire. The thing is, arc welding robots don't really like switching the wire out. They really prefer to have one. So they have to go through and they have to come up with a compromise, like what is the wire that's going to work best for all of them? Because when you're doing it manually, it's very easy that usually, the arc welder can go over and change it. So in many cases, you have an arc welding cell in that you've got this big wire basket, which is like sitting off in the cell somewhere in the very, very long wire feeder that's coming around trying to get it out there. So again, just how the services get from one location to another can be rather amazing. And it's just not easy to switch it over. There are some cases where I've seen that they have it, but it's very complicated. So again, you've got to look at what are all my variables. In some cases, you have to compromise to come up with what's going to be best. So, the type of material you have in the weld. So you've got to look at the two materials you're putting together, whether you're having whether you need a flux core or not in there to help the welding, and just kind of goes on and on and on.
Yeah. Yep. I think so. Are there any other topics you'd like to touch on today? We did see the X.AI announcement today, so I didn't know if you wanted to touch on that at all, or if there's anything else that you wanted to.
That's interesting. I mean, everyone was wondering if they had spotted the X.AI headquarters yesterday, and it turned out to be Apex AI headquarters that was in the camo of the Cybertruck. Or maybe it was that Elon really was kind of winking and saying, "Oh, there's something's coming up." So
yeah, that's how I read it, was that even though that was not X.AI's building, that picture where it was conveniently cropped to just show X.AI, that was an Easter egg for the announcement that came today.
Yes, yeah, it probably is. I guess what surprised me is like, oh, I thought this had already happened. So it's like, oh, so it's absolutely official. And I see there is a list of the co-founders, and my understanding is a lot of them are very, I don't know if you would say luminaries, but definitely have a lot of experience in the area. So let's say pretty solid bench. There are some heavy hitters. So it definitely means that they are going to be probably working on some impressive things. At this point, it's pure speculation on the approaches they're going to be taking, what problems they plan on solving. I don't think there's been that much in the press release. I know you had a bit of a discussion that today in Spaces on that. I know there was sort of one area of discussion where you were talking about AI hallucination and sort of the dangers of that. And it's like, well, it's is it a feature or a bug? And if you think about it, especially in the area of vision, we're talking about we're having this hallucination in vision, which we see things like Midjourney are basically doing. I mean, they're just this very rich hallucination, yet there is continuity to what's going on. And the human brain has evolved to do lots of tricks. I mean, first the thing is that our hands and our brains kind of co-evolve together, which is why we have the brain power. But there's the other thing, and that is the flaw in our eyes, the fact that we have a blind spot in our eyes. Our brain compensates for that. So it's taking it and it's filling in a part of our vision with something in the scene that it thinks is there. So it's tricking us. So a lot of times what we think is reality is not really real. Yet it does it in a very correct way to be able to fill in the missing pieces. And so sometimes you want to have that sense of, I don't know if you want to call it hallucination or creativity, that is really what you want an AI system to be able to have. Sometimes you need to be creative and not rigid. And at the same time, I wanted to be able to see, a car that's passing in front of me suddenly disappeared. And I wanted to understand that it didn't disappear, it's just blocked, which means there's a chance it may appear somewhere else. And so have it sort of imagine where it could be and where it should be, because that might be very important coming up, because, it's blocked by a large vehicle in front of me. But if I know it's there, certainly as a human driver, I'm taking that into account, that this is going to somehow affect the flow of traffic, if it's there or not. Or if it's a cyclist or if it's a pedestrian or something like that, that something pops up somewhere and you realize it. So you want it to be able to fill in these blind spots. You want it to be able to hallucinate a little bit. And that's why I don't see it as a bad thing. But obviously, it's one of those things we have to be able to tune, because sometimes if people hallucinate too much, they then become delusional. And then other times, if people aren't very creative, they become very rigid and they can't really find their way out of a very simple problem, because their thinking is just way, way, way too rigid. So, yeah, I'm sure there's some parameters that will need to be adjusted, but it's not a bad thing. I definitely see it more as a feature than a bug.
I didn't get to talk about this in the Twitter space today, but the commentary you just made, reminded me of, there's a field called interpersonal neurobiology that I've been interested in for a while now, and I haven't gone too deep into it, but it was started by a professor at UCLA who brought in a group of his colleagues from all the different schools. And so he was a psychiatrist, but he also brought in neuroscientists and mechanical engineers and computer science engineers. And their goal was to try and, the way that he saw it, the way that psychiatry works is all about focusing on dysfunctions. They've got the diagnostic, the DSM, whatever that is, diagnostic statistic manual or something. And it's basically mental health by subtraction, that we're going to say, well, we don't know what mental health is, but we know that it's not this, and it's not that, and it's not this. And so his goal was to say, okay, instead of trying to figure out what are all the things that are not mental health, let's define what mental health is and try and move in that direction. And, if we can positively move towards mental health instead of negatively just move away from not mental health, maybe we can have better patient outcomes. And through all of that research, one of the things that he came to believe was that there's really two types of dysfunctions. One of them is a function of rigidity, and the other is a dysfunction of chaos. And that there's this basically sliding scale in between, and that a healthy system maximizes, an unhealthy system, if you get disturbed from the median of your spectrum, that you quickly get pulled all the way to the dysfunctional end of this spectrum, either in a completely rigid way or a completely chaotic way. And that mental health, it's the goal of that is really to widen the window that you can operate and then return back to the equilibrium point without getting sucked all the way to the ends of the spectrum. And that's one of the things that I think we'll end up finding similarly with a lot of the, I think most of these AI systems are going to end up being analogous in a lot of ways to human minds, just because we're building them on maybe not an identical, but a very similar theoretical substrate. And so, yeah, I think that we do need to take into account, that creativity needs to be part of the system in order for it to have the capacity to be balanced. But then we also need, so what we don't have right now, at least with LLMs, is the grounding, the rigidity side of the equation to pull it back towards equilibrium once it gets a little bit too far over in the chaos or the creative side.
Right. And if you look at, heuristics are basically these rules that we put together to try to solve problems. The thing is, the heuristics ahead of time sort of determine what all the rules are, and because you can't break them, it can't think creatively at all. To get stuck in there. Mm-hmm. And so in many cases, it's thing like sheep. I understand that it's something like, if a sheep goes down an alleyway or something like that that's very narrow and gets to the end, it doesn't know what to do. It doesn't know to back out. It's just like, we'll just kind of sit there like, you don't realize you're kind of stuck. That's kind of this rigidity of not understanding there's a way to solving this particular problem. With a lot of heuristics, you're probably familiar with the Monte Carlo method. So the Monte Carlo method is like an attempt to try to come up with some creative thinking when solving a problem with lots of variables. So I got a bunch of variables out there, and I don't want to try an infinite number of combinations to find out what's going on. So what we're going to do is we're going to randomly kind of go for some here and there. And these variables, we're going to apply some rules on what we think is like a min and max values for some of them that keeps them from being maybe silly. But the thing is, you may not realize there's some combinations that really are kind of silly, and that you'll run these Monte Carlo simulations all the time. And this is what everyone who is doing their investment models, I want to look at my bear thesis and my average thesis and my bull thesis, and they put all those things in there. And sometimes when you look at them when they're out there, some of the assumptions they have for their bear or bull are just absolutely ridiculous. And the reason they're absolutely ridiculous is the Monte Carlo just rolled the dice, and in that particular case went for like the 5 sigma, mm-hmm. because that's a possibility of coming up. But you look at it and say, that's nuts. What do they think? You got to think about cutting that thing out. And that's what you kind of mean by the grounding, is that you will look at some of these models and you'll say, oh, that person's model is delusional. It's not really delusional. It's just that that's the way that heuristic works, the way Monte Carlo works. And the grounding is going to be the AI is going to know ahead of time. As soon as the dice roll that number, it'll just go, no, that's ridiculous. I'm not even going to bother to run that one because I know that's silly. Or it might try to say like, okay, why do I think that's silly? Mm-hmm. What's the rationale? Let's just try it once and let's see, And so every now and then you do want someone that will try what seems to be crazy at first to test the bounds, because he's been told it's a crazy idea, but it's only because that's like the norm of the society. It's not necessarily because it was first principles thinking. And so a lot of times you want to go back to that first principles and start saying, why is that a delusional idea? And then if you are convinced it's a delusional idea, don't pursue it. But if it's like, no, that's just because someone said a long time ago and everyone didn't question that person. So sometimes, yeah, like they say, question authority every now and then. You have to.
Yep. The I mean, Elon is a great example. He, to me, is a 5 Sigma person in human history, and so a lot of the things that he does are at that edge of just crazy distribution of possible outcomes that actually turn out to be pulled into reality. I mean, I think that's really the definition of what a reality distortion field is.
Yeah, but sometimes the reality is based on some sound fundamentals. And again, when I go to the example of what Professor Hopcroft was coming up with, is it was kind of delusional at that time when you think of the state of computing and what we knew and everything else. We could not do it with 1980s technology. But it doesn't mean it can't be done, and it can't be done today, because we know from a first principles standpoint, a person can do that. And if a person has enough intelligence to do that, why should we discount the fact that someday in the future we should be able to do that? It's just a question of the building stones that we're going to need that to get up to that level. And it might be that, we just have to wait, another decade or two for some developments to happen over here, but keep your eye out for them. So even if you don't have, you're not clever enough to do it yourself, you might see that emerging technology and you realize, wait a minute, this idea I had 3 or 4 decades ago, with this one over here, I can combine it together and move ahead. And that's, again, full self-driving. It's a hard problem. Everyone agrees it's a hard problem, but there's no reason why it can't be done. Now, we might argue that it's like, it can't be done till 2100 or 2200 because we need to have like the most crazy, ridiculous computing for it. Or you could say the argument is like, no, clearly by 2025, 2030, the latest, maybe even, sooner than 2025. So you can have that argument, but I don't think you necessarily have the argument to say it can't be solved. It can be. It's just a question of how hard is it going to be. Like going to the moon was crazy, but we've proved that it's a problem that can be solved. The only problem is it takes a lot of resources to be able to do it.
Yeah. One of the examples that I always love that blew my mind when I learned it was that we basically had early designs for gas turbine engines in the late 1800s. The problem was that we didn't have any materials that were capable of not melting behind a flame. And so it took us until the 1940s in order to be able to have the material science that was required to make turbine blades that could withstand the operating temperatures and pressures. And, once we had the materials, then we could go back to the ideas that people 60, 70 years beforehand had kind of pioneered and then build those out. And so that's one of the great examples of, how creative people can be and how far they can see things. Or, on the flip side, how imminently possible something is, except for one little tiny piece. And one then detail. You've got to wait until all of that comes back around.
Yeah, I agree with you that in material science, where I went to school, we had a pretty good material science school, but it was very small. It was part of the engineering school. And you could see the importance, and it didn't quite understand it at the point. Then later on, I start to see like a lot of these NASA text briefs, and you start going through it and you realize the biggest contribution NASA has probably made from the entire space program is all the material science that's come out of it. I mean, we talk about all these other things, but it's probably been more the strides we've made in material science and how it goes on. And it is the unsung hero. And it's one of those unsung fields or areas where not enough people really apply. So if someone's thinking of becoming an engineer out there, they're not sure, it's like, look at the material science program at your school and go into there, because if you look at what's going on in SpaceX and Tesla, I think almost all the miracles that come out of there in the end because they've got some guys and gals that know what they're doing with material science. The GigaPress,
Yep.
without the algorithm, no, that doesn't work. A lot of the other stuff that SpaceX is trying to do, some of the alloys and materials are coming up with, you need to do it. So you're absolutely right. Material science is extremely important. And then the one problem that you then have with the material science after that is, not only how do you form these things, but you figure out how do you actually fasten them together? Because sometimes you'll have these disparate materials that, how do they actually form and come together, and looking at the fastening. And that's where the mechanical engineers come in and try to solve little problems like that. So, yeah, you need all of those things to be able to be fully functioning in a high technology society.
Yep. Yeah, it's incredible what the aluminum alloy is capable of doing in the GigaPress. Like, for them to be able to fill that cavity with hundreds of pounds of aluminum in microseconds, and for it to cool so rapidly and in such a way that all the crystal structures form without needing to then be heat quenched afterwards is, it's just mind-boggling. And so it's not and it's a combination of both the material science and then the quality of whatever their FEA simulation is that they're able, FEA and CFD, that they're able to do the simulations ahead of time to be able to get that to come out just right. It's like, that's a marvel of engineering.
Yeah, because if you don't get that step where you have to get rid of the heat treatment afterwards, then it's almost useless. There's no point. It will just slow the whole process down, and you're going to need these autoclaves and everything else to be able to do that, and maybe more quenching and what kind of surface treatment.
And you can't
preserve
the dimensional accuracy of the casting after, if you have to do anything to it afterwards, it's going to warp, things are going to move. And that's the whole deal. I love the way that Corey describes that thing. Once that casting comes out and it's perfect and you don't have to do any of that stuff to it, it's a stone. And it's the same every single time. It's a known stable interface of the highest quality that you can come back to. And it's the foundation that the whole rest of the car is built on. And it's a perfect foundation every single time. So it's fast to make, it's perfect quality. You can make it in such a way that the load bearing during normal driving, but also how loads flow through the material in crashes, everything can be optimized. You can optimize manufacturing, you can optimize material usage, you can optimize crash performance, all of those things. And all of that hinges on, I have the magic aluminum that's capable of being cast at this size.
And then to realize that a lot of times when you try to solve a problem, you're solving it the wrong place. So everyone's worried about the panel gaps, and they're we got to focus on the outer part. How do we get those panels in the middle? That's nothing with the panel gaps. It's all about your foundation.
Yeah.
Because everything was built up by hundreds of parts, and you can already see the stack up errors you're going to have in there. Is if you build a house and you have a really lousy foundation, the rest of your house is going to suffer. There's nothing you can do to get the house back in order if that foundation is cracked or flawed or just not set the way it's supposed to be. So again, they went back down to where the root of the problem is. And by having that, everything else just takes care of itself magically. You don't have to worry about it. You're not spending time chasing your tail trying to fix that. And then just to think about what they did in the body shop, eliminating all those robots and fixtures and end-of-arm tooling and robot programmers and floor space and everything else. And I was both giddy that they came up with that, but kind of sad. It's that's what a lot of my customers do. That's what my parent company does. They sell the robots for that, but they'll find places for those robots. So I'm not worried about the robots going extinct. They just, we have other areas that can be automated for sure. And that you just kind of put them on over there. So.
Well, this has been a really fun conversation. I appreciate you, Scott, and I love getting to kind of wander around and touch on different topics and nerd out a little bit. But I do think this kind of seems like a good place to stop. I don't know about you, but I'm getting hungry. So
Oh yeah, me too. And remember, I'm an hour ahead of you. So
Yeah, so it's 7 o'clock there.
oh, is
Yeah.
it? Okay. Yeah, it is. Okay. Yeah, it is.
Yep. So, well, thank you once again. I thank you also for everyone who is here and joined us in the live stream. Appreciate all of you. And I look forward to the next conversation. We'll have to get together, and I know that this is not a good week for John, but I do want to get together with you and John at some point in the future and have some more interesting discussions with the three of us as well. So
yeah, absolutely. I look forward to having John join us the next time, because usually he adds a little bit more life to these conversations and keeps them interesting. Try to do my best in his stead.
Well, and he's just a great educator too. I love his ability to bring things down to a simple level that a lot of people can understand. So
Okay, so once again, thank you, and thank you to your audience for joining.
Have a good evening.